All right, so how did the homework assignment go? Base converter thing? Simple? Trivial?
At first.
All right, so we're supposed to, is it just supposed to be, we have two screens, right? Decimal to base and base to decimal? And then I gave us the switcher already, right?
Yeah.
Let me just then go on to some other stuff today. We're going to do some C programming today. You'll like that. You're a C programmer, right? Oh. Do some C pro. You like C? Yeah, you only like Java because that's all you know, right? Yeah. You're a coward, Edwin. So I got no defense. It's all recorded. All right, so if I go to decimal to base, that takes me to that screen. If I go to base to decimal, that takes me to that screen. All right, which one do we want to do first? Fight to the death. All right, you said base to decimal, this one?
Yeah.
All right. Okay, so we're going to do base to decimal first. So this is the one where we have to divide. Well, actually, no. Base to decimal is when we take the start at the right-hand side. This is the ones place, the, if for binary, twos place, fours place, eights place, so on and so forth. Okay, so we're going to enter in some number here, and then we're going to choose between these four buttons which base that number's in, right? And it's going to convert that then to the decimal version, which will spit out here. Okay, so let's make sure. Do we have a preference if we want to have one function that knows who called it, or do we want to have four different functions? I like having four different functions. I don't like naming buttons, so I don't care what your preference is. So we're doing base to decimal, right? All right, so I already have the button presses for those, so this is having those things come up, so we already have this set up anyways. All right, so we're going to go ahead and we're going to grab the value that was passed in. Now I'm going to quickly just write my function for converting. All right, so create a little private function in here. It's going to return the decimal value. We'll call this guy base to decimal. And this guy is going to take as a parameter a string num as a parameter. All right, as well as a int. You can call it base, or if you want to be mathy, you can call it radix. All right, so whatever makes you happy. All right, so this function is going to be a generic function. We're going to pass it a string in, that's the representation of our number, and then we're going to pass it in the base that that number's in. Okay. And this guy will then go through and build up our decimal number. So our decimal number, we're going to have a sum. It'll start off at 0. We're going to sum a whole bunch of stuff, right? All right. Now we want to start. We're going to have a place. So place always starts at 1. The far right position is whatever the base is to the 0th power, which is always the ones place. All right. And then we multiply it by base as we go to the left. All right. Then we're going to have a loop that's going to travel num from the end towards the beginning. So we'll write that loop. So this will be for int I is equal to num.length minus 1. That's the last legal position in num. Keep going as long as I is greater than or equal to 0, because we want to go all the way to the beginning of that value. I minus minus each time. Okay, so this is going to take that guy on a voyage down there. Okay, now each time we go through here, we need to grab the current character at position I in num, and that guy's going to be a char. And I want to get the numeric version of that guy. Okay, so if it's the char 2, I want the number 2. So if I have something that looks like this, I need that to turn into a 2. If I have something that looks like this, I need that to turn into a 10. So on and so forth. That make sense? Okay. we're going to do a little trick here. I'm going to create a string in here called map. I'm going to fill the string up with all the numbers 0 through 9 and then the letters A through Z. Did I get all of them? Is it even possible to read the alphabet without doing the little sing-songy thing? A, B, C, D, E, F, G. You know what I mean?
Yeah. I feel like I've seen it.
And nobody, I mean, LMNOP, this just is like it's like a jump, right? It's almost like when I was learning the Tamil alphabet. Huh? No. I do know the Greek alphabet. I do know the whole Greek. Do you know the Greek alphabet?
That's the whole thing.
Alpha, beta, gamma, delta, epsilon, zeta, eta, theta, iota, kappa, lambda, mu, nu, xi, omicron, pi, rho, sigma, tau, upsilon, phi, chi, psi, omega. Now the funny backstory is where I learned that was in, I think it was in 7th grade. They don't do this in schools anymore, but we had a teacher that if you you had to memorize the Greek alphabet and you had to see how many times you could say it on a burning match. Because you had a kid standing in school with a burning match saying the Greek alphabet as many times as they could before they burned themselves. That doesn't seem like it goes in schools anymore, does it? That doesn't happen.
I've heard of that.
Yeah. That's back when I used to spank kids too.
Yeah.
Man, my 1st grade teacher. 3 times. 3 times I had to go. I remember the route too. You come out, you go right halfway down the hall, you have a little door on the left, there's a single light bulb. And they got the beating instrument on the wall. I wish we had that in this class. All right, so I have this string that's going to be all of my numbers, 0 through 9, and then all the letters of the alphabet. All right, and you can assume that you're always going to get an uppercase letter, but we can always just convert to uppercase as well. All right, so in fact, I'll go ahead and do that. I'm going to say num is equal to num.to uppercase. That'll guarantee num is all uppercase. If you didn't do that, that's not fine. That's not a problem. You can just assume that they always put in uppercase letters, or if you did lowercase letters for your hex, that's fine too. All right, so at each bucket, I need to get the value of these. So there's a function for strings called index of. All right, the index of function. If I say give me the index of 0, the char 0, it'll return for me 0, the first position in the string where that was found. Index of A will be 10. Index of B will be 11, so on and so forth. So that'll give me a number. That makes sense? Otherwise, you could have written a fairly scary collection of if statements. If it's the char 0, return a 0. If it's the char 1, return a 1. If it's the char A, return a 10, so on and so forth. You could have also done some stuff with the Unicode value of these and gotten the value as well. But the cool kids would do either the Unicode thing or this. This is what a modern programmer would probably do, use the index of tool. All right, so now I can get that value. So what I'm going to do is I'm going to say sum is equal to sum plus. And I'm going to add to that a value. The value is going to be whatever the numeric value is of the character I'm currently looking at. That is map.indexof. And I'm going to pass it num.charat I. All right, so that's going to give me a number times place. And I'll add that to my running total for sum. So this guy right here gives me the numeric version of the character I'm looking at. If it was an A, it'll give me a 10. If it was a 3, it'll give me a 3. Char 3 becomes the number 3. And I'll multiply it by place. All right, then we make place b, we multiply place by base to get it 1 bigger. If we're dealing with base 2, it'll go 1. 1 times 2 is 2. Times 2 is 4. Times 2 is 8. So on and so forth. So place just keeps getting bigger and bigger based on what the base is. When all is said and done here, our final answer is stored inside of sum. All right, so this is the logic for base to decimal, right? Okay. So now we need to grab our input ET. So no matter which of these guys we get, we're going to get the string from input ET. And we're going to call our function here. We're going to output it to answer TV. So I'm going to say this dot base to decimal, I'll call it 2 base to decimal, and I'm going to pass it my string. My string is going to be this dot input et dot get text dot toString, right? So that is the stuff that's in that text box. And then I'm going to pass it for this particular function a 2, because that's the base that that guy is in. This guy is going to give me an answer and I'll go ahead and I'll throw the answer into my text box, or my output, rather, answer TV. So I put this all into one thing. If you want to feel better and break it into little steps, you can say string input is equal to this dot input et dot get text dot toString. So now you have the string. Then you can say int answer is equal to this dot base to decimal, passing it input, passing it a 2. And then you can set your thing here to whatever answer was.
So when you put base 2, it's actually putting that 2 up to the top.
That's getting passed in for the base here.
Okay, because it's column.
Yeah. And this is actually something Android Studio does, this little base colon thing. Yeah, that's not traditional Java. It's like a helper little thing. So my base to decimal function takes 2 parameters. A string representation of a number, and then what base that number is currently in. And it will always spit out the decimal version of it. All right, so if I'm doing this for base 2, it's going to look like this with base 2 there. I'll just steal this for the other ones just to be done with it. So I'll steal those 3 lines, paste it in here, change the 2 to an 8 for octal. Change the 2 to a 10 for decimal. Change the 10 to the 2 to a 16 for hexadecimal. That makes sense? All right. Let's go ahead and test this guy. We just did base to decimal, right? All right, so if I put in my favorite, why is it? Oh, I get it. Activity, decimal, base to decimal, design. This guy's keyboard needs to be different keyboard. Oh, this would be a good one. Text cap characters. Then you wouldn't need, oh, actually, then it'll be harder for me to type it in. We'll just do that. Okay. Now I can run it again. Otherwise, it was only giving me a keyboard with numbers in it, so I couldn't give hexadecimal values. All right, so we'll do my BAD. And that's in base 16. There's my 2989. If I want to change that to 101101, or whatever. That's the number 93. If I want to say that's an octal, it'll still give me a value. It's a big old octal value. 64 an octal, give me a 52. And 2134 in base 10 is 2134 in base 10. All right, that makes sense? So maybe if you were nice, you would zero out this edit text after it to make it easier to put a new number in. But, you know, pick your poison, whatever. Okay, so that is base to decimal. Questions about that side of it? All right, so now let's go and do the decimal to base side of it. That's this guy. Let's go ahead and write our function here, private. Now this guy's going to return a string because we're going to be building up a string that's the answer. So it's going to be private string decimal to base. And this guy's going to take an int num as a parameter, as well as an int base that we want to turn it into. Okay, and what we need to do is we need to continually divide num by the base, recording the remainder on one side, and then recording the quotient on the other side. It's quotient, right? Is that the right word? Quotient? Yeah, quotient. All right, so we're going to have a string answer. And remember that you read your answer from bottom up. So you can either build it backwards or you can reverse it at the end. So I'm going to build it backwards. So we're going to say string answer is equal to the empty string. And I'm going to say while, I'm going to keep going until num finally whittles down to 0. All right, so I'm going to say while num is greater than 0. We're going to keep doing some stuff. All right, so the first thing I'm going to do is I'm going to record the remainder before I change the value. So I'm going to say answer is equal to, and I want to get the remainder of num mod base. And I'm going to concatenate onto that answer. So that's me building it backwards. So instead of saying answer is equal to answer plus num mod base, and then having to reverse it at the end, I'm just going to build it in reverse. And then I'll say num divide equal base. That's num is equal to num divided by base. So make sure you grab your remainder first before you change num. If you don't like these compound operators, then this is num is equal to num divided by base. That's what that guy is. All right. Now, when we're done, when num is finally 0, so we had num is equal to num divided by base. It finally became 0. We had already recorded the previous remainder, right? Then we're done. So we're going to go ahead and we're going to return answer. That should be it. Ah, so now we need the map. Same thing as we had before. In fact, I'm going to steal it so I don't have to type the whole alphabet again. Steal this little dude here. All right. Now, when we go to concatenate this on, rather than just taking the number here, what we actually want to do is we're going to say map.char at that number. So if I say map.char at 10, that'll get me the character at bucket 10, which is an A. Map.char at 3 will give me the character that is a 3. Map.char at 15 will give me an F, which is at bucket 15. Make sense? So char at is like the inverse of index of. All right. So this would have worked for anything before. It would work for anything. It was base 10 or less. Now it'll work for all of them. Okay, so that's my decimal to base. So now we just need to go in here. And this is for base 2. So we're going to grab our decimal number. So we're going to say string num is equal, actually it's going to be an int, right? Int num is equal to integer dot parseInt, and the integer we're getting is, and notice there is a second version of parseInt that takes that would have done this logic for us, but it was easy enough logic, so good practice. So integer dot parseInt, we're going to pass it the string that we're reading in. So this is this dot input et dot get text dot toString. So that'll get me the integer version of the decimal number that was passed in. Then I want to go ahead and get my answer. String answer is equal to this dot decimal to base. And I need to pass this guy my number, so there's num, as well as the base. This is base 2 for this function. And then ultimately, this dot, what did I call my output guy? Answer TV dot set text to answer. Like that. Here's the integer version of what the user entered in. Here's what our decimal to base returns for that number in base 2. Then I'll set my answer TV to that guy. Steal those 3 lines. This is for base 8, so change that to an 8. This is for base 10. Change that to a 10. This is for base 16. Change that to a 16. All right, let's go test this guy. So this is decimal to base. So if I do 2989, I say convert that to base 16. There's my BAD. If I say base 10, there's my 2989. If I say base 8, that's what it is in base 8. Base 2, there's my crazy base 2 number. All right, anything else you were supposed to do, or is that it? Okay, so good practice, got to write some algorithm stuff, got to use some Android Studio stuff. All right, so questions about any of the conversions stuff?
Not in conversion, not in Java. When a function, when a method returns a string, in Java, does it give the address or does it copy the address?
That's a good question. Well,
Because in the C character, it just returns the
yeah.
address.
So this is the deal. In Java, all objects are pointers. So in Java, it gives the memory address. But, okay, and this comes down to how whenever you print a string. Here, let me actually see if I can show you. Let me see if I can fake it here, actually. Just so I don't have to do it in here, let me just go out to a terminal and do something. Here, I'll just use this one. So I say string s is equal to hello, something like that. When we say system.out.println s, it prints out hello. Now, in the same vein, if I say randomr is equal to oh my gosh, come on, we got this. New random, I need to import java.util here real quick. And I do system.out.println r, I'm going to get a weird memory addressy looking thing. Okay? Both of these guys are objects. In fact, if we want it to really look the same, rather than using the shorthand thing here, we'll say new string, like that. All right? So this guy's an object, this guy's an object. When I print out S, it's going to print out hello. When I print out R, it's going to print out some weird looking memory address. So let's prove that real quick. All right, so there's hello, there's crazy memory address. Okay, so your question is that when we're using strings, is it passing the memory address or not? And let me just test this before I want to see how deep the farce goes with. So if I say print out the object version of S. No, goes too far down. Let me do one more thing. Now it's all the way down at the base level. So let me show you this here. So if I go to the Java documentation, whatever. They changed their format for 9? Yeah, they did. All right, so let's just open up java.lang. Actually, I want to do, yeah, it's in java.lang. Go to the system class. Go out, and here's all the printlns. What did I miss the list of? Oh yeah, they were up here. Oh, I'm sorry. I clicked the wrong thing. There we go. Okay, so notice in here, I'll just go down to the printlns. There's a whole bunch of println functions. That this guy knows how to print a boolean, a char pointer. This guy knows how to print an object. I was trying to force Java to treat a string as an object to get the memory address version of it versus a println that takes a string. Now the thing is, if we go to object here, all objects have an innate method called toString. This guy right here. All right, so the reason why it was, so for a generic object, we're like the random class that we created an instance of. It called his toString method, and since the random class didn't implement their own, you got the crazy memory address. The string class actually does have his own toString that spits it out. So the short answer to your question is it's an address. The problem is that we don't have a way in Java of getting that address of a string because they kind of hide it from you. And we can actually prove it this way. Okay, so I'm trying to trick you. Okay, so I'm trying to trick everybody here. I have 3 strings. They're all equal to hello. S2 equal S3. What should this output? True or false?
False.
You think false? So I want to know what's the output of this program going to be. I've defined 3 variables up here. I haven't even used S anywhere. I'm just using S2 and S3. And I said, is S2 equal to S3? He thinks it's going to be false. Who wants to agree with him? Who wants to? Anybody think it's going to be true? That they are equal? How confident are you? How confident are you?
what's printed?
Yeah, what's it going to print? You said false.
It will return false.
Are you confident?
I don't know how this system printer behaves. I mean, the print, because it's written in Boolean type.
Well, yeah, so fine. If you here, if it'll make you feel better, Boolean answer is equal to S2 equal S3, and then we'll print out the answer. So answer is going to be either true or false. You think it's going to be false? Are you confident? Willing to bet your grade on it? Who else is willing to bet their grade with him? You'll be looking for some extra credit. Yeah, that's not what we're doing here. But he knew we weren't doing that either. So here's the now hold on. You get a second chance. There we go. Okay. So now we'll change this to S is equal to S3. What's the output going to be? He was way more confident the first time.
Yeah, now it will be false.
You think it's going to be false now?
Because it's treating.
Why it was true in the earlier
I'll explain. This is actually a really important thing. Something about Java, and it's related to what we're going to talk about today. Java hides a lot of stuff from the end user. And you mentioned that to compare strings, we need to use dot equals, right? But you don't know why, right? So we're actually seeing how Java really works under the hood, under the hood here. So this is going to give us a false. Okay, they are not equal to each other. I'll explain why here in a second. All right, so there's our false. So, well, now he's just back to, like, I mean, he failed the class with his first thing, his overconfidence, and now he's just right back to ground zero. I mean, he's lucky I gave him a second chance. Otherwise, he would have had the next 13 weeks off, 14, however many weeks we have. What would you have done with that free time? Be at my office. Learn Java. All right. Let me show you a picture here so you can see actually how this works under the hood. That's not this class. We're 548, right? I do know programming languages almost as well as I know Tamil. Yeah, I mean, ask me any question about verb conjugation in Tamil. Does Tamil have verbs? is that a thing? All right, let's see here. I'll just throw it here at the end. Okay, so we have three different lines that we had here, right? We had string s is equal to new string hello. Then we also had string s2 is equal to hello. And we had string s3 is equal to hello. So those are the three variables we created. All right, that makes sense? Now, this is where things get a little wonky. Let's start off with this. What does the new keyword do? In Java or in C++, what is the new key, or in C#, what does the new keyword do? Gets memory. Yeah, this is a memory thing, right? All right, so we're going to create a new spot in memory here. So let's just say this is memory address 100. And in memory address 100, we're going to have hello. And of course, memory addresses are in red and values are in green. That only makes sense. All right, so there's my variable s. Forget about the capitalization. That's more of a whatever. So we would say that s holds a memory address, and it points to memory address 100 where, for example, 100, where the string hello lives. Okay? Now, this is where the real problem is. And this is kind of
I
the...
understand.
All right, so we're...
It's a string literal. We are addressing the assigned address on the string literal.
Yeah.
Those two addresses are same. Here, this is a different address.
Yep. So I'll keep going with this. So here's the deal. If Java is the first language that you end up learning, you're actually kind of doing yourself a disservice. And it's actually kind of the purpose of a course like this, where we're trying to look at what's under the hood, how computers actually work. And in order to understand this, you really have to understand an older language like C and really understand how strings are stored. Now, if you came from a language like C++, let's say, but you learn C++ kind of at the academic level, or at maybe let's call it the applied level rather than really the theory level, understanding how the language actually works, you might look at something like this and say, oh, that's so nice of Java. They gave us this kind of shorthand for strings. Because in Java, strings are really important. We use strings all over the place in Java. I usually say that strings are very malleable in Java. Once we have something in a string, we can do all sorts of stuff with it. We can convert it to an int. We can easily work with strings in Java. So because they're so important, Java gave us a nice shorthand syntax for working with them. I didn't have to use this whole big long rigmarole of new string, blah, 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 like I do for every other object in Java. Strings are the only object in Java that you don't have to use the new keyword when you're creating them. All right, they're the only one. Now we see here we can use the new keyword if we choose to, but we don't have to. So we might think that, oh, Sun Microsystems, makers of Java, they were just being nice to us. A lot of times I'll refer to this type of thing as Syntactic Sugar. So they gave us a kind of a friendly syntax, Syntactic Sugar, all right, where this is equivalent to this. And the reality is it's almost equivalent to the guy above. Because what happens here is when we first define S2, I'm going to steal this guy. So we have S2. Java maintains a literal space. And it's going to go and look up all of its literals. So for instance, it knows about the number 0 and the number 1 and the number 2, the literal values. And it's going to say, do I have a string literal that's currently equal to hello? The answer is going to be no, I don't. So it's going to create a new one. Maybe that's at memory address 400 and put hello there.
In this segment,
Huh? It'll be in the Java virtual machine's own memory segment for a literal space.
we have stack, heap, all these memory segments.
Yeah, but since Java is a virtual machine, it's all done in software. You don't have direct access to the underlying data structures. So now we go to create S3. Create S3. We're going to ask the question, is there already a string literal named hello? There is. So we're going to make S3 point at that guy. S2 is equal to S3. They both are equal to 400. It's not that they're both equal to hello. When you use the double equal sign, that's the primitive comparison operator. We're saying, is S2 and S3 the same thing? Are they the same memory address? In this case, they would be because they both point to the same place. But when I said, is S equal to S2, that's saying is 100 the same thing as 400? It's not. Now, what Edwin pointed out is if I come back in here and we go back to the previous thing where I was saying S2 equal S3. Actually, I want to say, let's just keep it this. If I say S equal S3, I'm going to get a false. We just saw that, right? But if I change this to S dot equals S3, now I get a true. Because dot equals says compare the contents of S3 to the contents of S. I'm looking at the strings now, not where they live in memory. That makes sense? So that gives me the true. Make sense? So that's actually something that's a little bit dangerous about learning a language like Java first. Java is a very friendly language as your first language because it doesn't let you get into too much trouble. You know, when I teach introductory programming classes, I kind of talk about the history of languages and the weaknesses of older languages. Like here's C, this is what C was good for, and here's where it started showing its weaknesses. So then we have C++. Well, where's C++ weak? Well, we're going to be dealing with this stuff today here in a little bit, but when we talk about C++, the weakness I point out is that C++ empowers the programmer to make bad decisions. All right, so, and what I mean by that is, if you're having a party at your house and you're inviting me over to your party, do you hand me the house and tell me to open the door at 8? Or do you give me a little piece of paper that has your address on it and tell me to show up at 8? Which makes sense in real life. If you're inviting me to the party, how many of you would hand me your whole house? That makes no sense, right? Doesn't make any sense. So you would all hand me a little piece of paper, or at least tell me what your address was so I can go find your house. Correct? All right. Let me just check something here real quick. Yeah, we talked about cost of memory. All right, so consider in an older language like C or C++ and the time period. This is in the late 60s, early 70s, even mid 80s with and into the 90s with C or C++ rather. Memory was really expensive, so handing somebody a house would have been detrimental. Okay, now in real life houses are heavy, so it's going to be detrimental anyways. But one of the jobs of a programming language is to allow us to solve problems in a similar way to how we already think. So we would say in real life it would never make sense to hand somebody a house because houses are too heavy. It would be too expensive for us to hand somebody a house. We would break everything, right? Well, that would be very, very true in the 70s or 80s, whatever. If we presume what's the memory requirement to hold a house, it would be high, which means very, very, very expensive, like we talked about, I don't know if last class or the class before that. Now, the situation is a little bit flipped today, right? Because memory is a lot less expensive today. So maybe you can say that it would never make sense to pass something by, to pass a house by value. It would never make sense to actually hand somebody a house in real life. But maybe we could create some sort of scenario in a programming language, because programming doesn't, when you're working with computers, it doesn't have to mimic real life. Often it does, but it doesn't have to. Maybe we can make an argument of why in a particular situation we might want to send somebody the actual house, not the address of it. Okay? In a language like C++, we could do that. But in a language like Java, we can't. Java takes that decision-making away from the programmer. Java says that all objects are passed by reference. You get the memory address. Okay? It protects strings so far as it says you can't see what its fake memory address is. Because with Java, all the memory addresses are fake because they're actually addresses inside of Java's virtual machine, which has a piece of address space of the actual computer it's running on. So they're not even real memory addresses anyways. It's the fake ones that the virtual machine handed out. But we don't have a way of getting at the memory address that is actually stored in a string because the language is built around the string data type. But it is still an object, therefore it is still an address. We just can't view it. All right. So a language like Java becomes a little bit dangerous because if you learn that as your first programming language, you don't know about those other things. You don't know about the problems it's fixing for you. That make sense?
Here, when you go to that second statement, string s2 equals hello. So why does it creating another copy since we already have a hello there?
I understand what you're saying.
Because of different structure?
Yeah. This is in the user space. The user specifically used the new keyword to request this. This area right here, big money.
It's just saying like, oh, we already have this, so we'll just use it space, the same space to save on space.
Yeah, so this guy would be called literal, let's call it literal segment. He used that word. I'm not sure that Java actually calls it that word, but let's see, top and left. Oh, whatever, center's good. So this guy would be kind of a special literal space for the virtual machine. And when he didn't find hello in there, because this guy would immediately be flagged as a string literal. So it's going to look for that string literal stored somewhere, not the user's string that they created that happens to hold a string literal, but since they explicitly said, I want new memory.
So I assume when we use the first line in some method, and when the function execution is done, I assume that will still be in the memory. First one.
This guy?
I assume.
Well, this guy would still be in memory as long as this guy was still in scope. If you define this inside of a function somewhere, when that function ended, this would be automatically garbage collected.
Which one?
The S, so this guy right here. He would disappear. Now, actually, you ask a good question. I'm gonna ask it a little bit different way. So it's a good question. To me, it makes sense that it would still exist. I'm going to create a second function here. All right, and this guy is going to be static void make. Actually, let's do static string make literal. All right, so we'll go ahead and, actually, let me think about this. Because I'm returning that, it wouldn't necessarily go away. All right, I'm going to do this. Okay. Then I'm going to come up here. Okay. So I'm going to call make literal 2 and I'm going to pass it S3. Okay. So make literal 2 is going to, S3 is going to get passed in here. So that should be my first literal version of hello. I create a new literal version of hello, which we presume should be equal to it. So when we print it out, this should say true. Then, I'll call make literal, passing it s. So am I actually testing what I think I'm testing here? So if I say make literal and I pass it s, s lives and dies with this function, but as long as it's alive here, it hasn't been garbage collected. So this should be true again. So that doesn't really test what I wanted to test. What I want to test here is when this function ends, but since we can't see the memory address of it, I can't see if it's the same. And if I return it, then I think that the literal space would stay intact. It wouldn't erase it. So what I'm trying to get to happen is I'm trying to get a scenario like this, where we create a literal, it's there. Then the function where s2, for example, was a local variable, that function ends, which means s2 gets garbage collected, which means that this hello is now gone, presumably. So then if I create it again, would the s3 that I created actually be in a different memory location, because it's the first time that that string literal hello is being created, because the previous one was garbage collected, because the scope of s2 disappeared, something like that. But there isn't a way for us to get at that memory location. So it's unfortunate. We needed a language like C or C++.
Why I asked this question, because you are written string there. I thought string is like a stack variable. Once the function popped out, if that returns just an address, you can't access in the program.
Mm-hmm.
The reason all this has come, because in a string, when you declare a static character array, which is a stack variable, if you just return an address, you will get undefined behavior, because that's on the stack memory, and once the function pops out, that will be go off. I mean, that whatever the function address will go off the memory.
Right, but the difference is that in an older language like a C or a C++, they didn't have literal space for string literals. In fact, strings didn't exist in the language. They just a character pointer was a string. So every single time you created a string, it was new memory. Yeah. So we weren't able to create the same scenario here. It would be, man. Let's see.
Is Java more efficient?
Oh, it's not. It's probably actually less efficient from the perspective of runtime, because it's running in a virtual machine. It's being translated. But at the same time, Java takes a lot of the decision making away from the programmer, which, let's say, from a programming productivity perspective, it's probably more efficient. But
you don't have to frame memory.
Yeah, but the programmer themselves, maybe if that's the first language they learned and they didn't take like a special interest in trying to understand how things actually work under the hood, wouldn't necessarily be aware of what magic Java's doing for them to make X, Y, and Z work. I want to search for something here. I don't think there's a way to do it, but let's see. Java show memory address of string. I tried to force it. Printing the address of a string instance. So we can say integer.toHex string and get S's hash code. Let's try that. It's going to give us something a little different, but it should give us the same. If they're the same, it should show it how it works. All right, so integer. I'm just going to steal this here. Oh, actually, we're okay here. I'm not going to create the one here. We're going to call make literal. And make literal, and these guys aren't going to take any parameters. They're just going to get created, and they're going to do their thing, and then they're going to die. So string s is equal to hello. Then we'll print out the hex string of s dot hashcode. Steal this. Okay. So we'll call make literal, then we'll call make literal 2. Make literal will create a string. This should be the first time we have a string literal hello. Then we'll print out the hash value of that. So that should give us the memory address of that initial literal space. Then this function ends. So garbage collection will occur. Therefore, we'll find out whether that guy actually disappears from literal space or is he reused here. If this call, make literal 2, gives us a different value, then that means that literal space is garbage collected, and we'll get a new one added to literal space. If it's not, and I suspect, oh well, what do you think is going to happen? You think it's going to be a different address? I think it's going to be the same address.
How does it fill addresses?
Because we're not using it anywhere, we're not returning.
Now, I know. I'm just trying to think from a language perspective. If Java's creating literal space, it would be more efficient for them to, if you already have a string literal called hello, why get rid of that from literal space when it might get created again in the future? Your argument, and you could be right, so your argument is that it's better to be a good steward of memory and clean up memory that you may not use again.
Performance versus memory.
Yeah.
It can be classified as write over, so it stays there until it needs to be used. So,
actually, potentially, that would then support my argument.
That's what I'm saying.
Yeah,
Like,
but the issue with that is in order to do that, it would still have to sort of kind of mark it as being used. It wouldn't be able to say, like, well, I'm going to keep using this memory here until somebody else needs it. You know, it's going to either say, okay, I'm going to have this string literal hello here, and literals are permanent for the run of this application. Yeah. I'm going to stick with what I said, but I actually think he's right.
I'm going to go with what you said.
I just have a hunch. I actually think I'm going to be right. I think yours makes more sense, but you're right. I mean, he hit it on the head when he said it's a question between memory efficiency and performance.
Well, right.
It would be higher performance to retain a string literal once it was created, but it would be memory inefficient because you may never need that again.
But like, why would you need that memory if it's not being used? Like, if it's something stored there and it's not, that memory isn't needed, what does it matter?
Yeah, right. I get what you're saying. The question is then that becomes a chicken or the egg problem, because you're saying, look, I don't need this right now. I might need it soon, but right now it's not hurting anybody to have this dude sitting here. Right. So if later on somebody comes in and says, okay, I need some more space, and I didn't have any free space, then I'll go, gonna kick this guy out. He'll get garbage collected then. It's almost like a delayed garbage collection. See, I hope he's right, because that would make me right.
It gets marked as garbage, but it's still technically in there.
Yeah, That would require a hybrid approach. Then we have to think about, I'm actually pretty confident you're right. But here's the reason. You got to think, when did Java come out? Java came out in the around 94 or so, 93, somewhere in that ballpark. Memory was still pretty pricey. People were still kind of nervous about memory consumption. So it would make sense if your son microsystems at that time, you'd be paying attention to memory. If a language like Java came out today, brand new language, where we have, let's call it infinite memory, for all practical purposes. It's not that you couldn't create something that would make you run out of memory, but memory is cheap now. Perhaps that decision would become different and a performance decision would make more sense, especially in a situation where you have a language that is on a virtual machine. So the language already has an inefficiency built into it. So because it's running in a virtual machine, it's running through a translator that's sitting between it and the hardware. So maybe today you say, okay, well, this is already slower anyway. So if I could just, because memory isn't a big deal, if I could just make this decision over here gives the nod towards performance, I'm improving the language because I don't care about memory. But because of the timing of this, I think memory was still important. So I suspect we are going to get different values printed out here. Because the first one, make literal, will get called. This guy will get created. We'll print out its address. When this function ends, that literal space will be garbage collected. We'll come back here. We'll call our second function. We will create a new hello literal, which will get added in probably a new address in literal space. There is a possibility here it might get the same address if it's the first literal we've created. So let's just see. I might not, if I end up being right, if that's not, we can't take it to the bank yet. We should probably create another literal in between here, just in case, to bump it. Right here, we'll do that. Well, let's just do it solidly, because I actually think he's going to be right regardless.
It would be interesting if whatever the computer's writing to it is just like an overwrite mode. And so like anything marked for garbage, it just overwrites it.
Yeah.
That would be efficient. Wouldn't that be more efficient? Because then you don't even have to get rid of it. You have to mark it or actually delete it. You just mark it.
Well, it'd be more efficient memory-wise, but now you've added kind of an additional responsibility for the garbage collector because now it's like situational garbage collection. Okay. So now you have this extra guy who's having to pay attention. Big money.
Same.
All right, hold on. We got to test this. Okay. I got to... break the literal. And we'll even have that guy be... actually, we can't have that be hello. So it's possible it got the same address because it was the first literal twice. Yeah. But that's the first position in literal space. So we'll go ahead and insert another literal there in the middle. And then see if it creates the hello literal in a new spot.
Okay.
See, I don't know if I trust this.
Like, what does it have to do? Does it have to go through another step to actually delete it? Because, like, if it's a process to actually delete something, then wouldn't Java have made it? So
let me test something again. So notice that these values are identical, right?
Yeah.
I want to try something here.
It's a different length.
No, just a different string, because a hash value is a one-way cipher. You have arbitrary size input, and it spits out to a fixed size output.
Okay.
So I want to see if we get a different value here than this. Those should still be the same, but I want to know if it's a different value. Because I want to know if that's a true memory address or if that's reflective of the content of the string.
Oh, okay.
Yeah, that's the content of the string.
But also, like, isn't the content of the string, it's going to require a different address based upon it?
No, not necessarily. Because definitely not with character pointers, because they're going to go.
That 4 kilobyte chunk?
It's going to be a pointer to someplace else.
Oh,
Yeah, we're going to talk about that in a little bit when we deal with some of the C stuff. Yeah, so this really doesn't give us a memory address. It gives us a hash. So you could still be right here. All right, hold on. Oh. So
Can you overwrite to string?
you can't because it exists at the object level. String overwrites it. We're not going to be able to test this. So I'm right, but for the wrong reason. The way literals are stored, because, and this goes back to we were talking about it's a virtual machine.
Yeah.
So it's fake memory, right? The way Java stores literals is in a position, they have a literal space, and it's just a dictionary. It's a bunch of name value pairs. So we're calling this guy a memory address, but it's actually just a hash value.
And a hash value is.
So a hash value is just a unique number. So we can think of it being like a memory address, but it's actually a hash value, and it comes from, so with the way they do their literal space is the literal for the string hello would be associated with the key that is the hash value of hello.
Okay.
So it's no matter how many times you create a hello in literal space, it will always have the same address because it's always going to hash to the same value.
Well, how is that more efficient for Java to do that? By creating a hash value, then they.
Well, it's not necessarily more efficient. It's Java is creating a fake memory space on top of the real system's memory space, and they just decided why not use hash values for that.
Okay.
So
everything gets converted to hash value pretty much when it gets stored.
Which actually then becomes interesting. This takes us down a really.
What about collisions?
Yeah, that's what I'm saying. Crazy. So hashes technically it's possible to have a collision. So if the nature of a hash value is you have an arbitrary size input, doesn't matter how big the input is. It could be 2 bytes, it could be 4,000 gigabytes as your input. And the output is always the same size. Okay. So for instance, MD5 is a famous hash algorithm. Message Digest 5, a lot of times you'll see it like when you download a big file off the internet. It'll also, on that screen, it'll have the MD5 hash, so you can kind of validate your download. You just downloaded 13 gigabytes. You can run that through the MD5 hash to give you this 256-bit value. And as long as your 256-bit values match, it's extremely likely that your download was not corrupted. Okay? But now having said that, if you have 256 bits as your output, that means there's only 2 to the 256-bit unique hash values. Make sense? So if you only have 256 bits to work with, there is a finite number of numbers that you can represent in 256 bits. But if your input is arbitrary, then there's an infinite number of inputs. So if you have an infinite number of inputs and you're mapping them to a fixed number of outputs, somewhere in there you have a possibility of having 2 different inputs giving you the same hash value.
Well, is that hex there? Is that like?
Yeah, I mean, the hash value is just represented in hex. under the hood, whatever hash they're using is some number of bits. So if you think about this as hex, this is 4 bits, 8, 12, 16, 24, 32. So that's a 32-bit value. Because a hexadecimal takes 4 bits to represent 0 to 15. Yeah, so they're showing it in hex, but under the hood it's binary. So that means technically we could discover a string literal. It might take us a while to find it, but if it's only using 32-bit space, it wouldn't be that bad. That's only 2 to the 32nd. That's what, 4 billion?
Yeah, 4 billion.
So we got 4.3 billion possible outputs. We just need to find 2 strings that hash to the identical to the same one of those 4.2 billion. And we just broke Java. Because now you have the situation where you have a program where you cannot have those 2 string literals existing in the same program together. Because they'll both map to the same hash. They'll overwrite each other.
So my thing is, like, then how do they determine what the hash or what a certain thing gets for a hash? Because, like, surely there's been a crossover between all the programming that's done ever in Java. Like, some person wrote this and some person wrote this over here. Different programs, but still the same hash. So, like, what caused them to get the same hash?
Well, there might not actually be, because MD5, so most hashing algorithms, so this idea of collisions is a known problem.
Okay.
So most hashing algorithms, and MD5 is kind of, let's call it the popular consumer one.
Okay.
They have what's called collision avoidance or collision resistance built into them. So it's possible that Java detects, sees this, tries to see if you have that hash value already in existence, and does the string also contain the same value? If not, maybe it has a backup plan where it adds something to give you a new hash for it. I don't know, earmarks it a different way. Maybe they do something like, maybe there's 3 different ways they do it to really minimize the chance of a collision. Because you got to figure, if you're going to have 3 collisions, you're going to get 3 collisions in a row. I mean, we're talking astronomical numbers at that point. But technically not impossible. Technically not impossible. I mean, this kind of goes back to like the cryptocurrency stuff, like Bitcoin mining. Because it's what they're doing and all that stuff is generating hashes,
right?
Generating hash values to compare this hash value to this other thing. Well, if you're your guy barely has any computing power, well, you might just guess. You might win the lottery. You might guess the hash value in your very first try.
Okay, that makes way sense.
Yeah, so it's very interesting. I'm sure Java has some level of security built in there for it, but it is interesting to see that their literal space maps on hash values based on the content of the literal. Like, what would have made more? I don't know. I guess you could still have the problem. I was going to say, if you do some sort of combination of the contents of the literal plus maybe the current millisecond hand on the clock or something like that, then you add some more variability, because then you could potentially have, that would have allowed us to have, if it was garbage collected, that would have allowed us to have 2 different values. Because, hello would have hashed, well, hello plus the current clock time would have hashed to a certain value. And then it would have been garbage collected. And then the next time we would have had hello, same content, but with a different clock time, which would have hashed to a different value.
But then you can also run the risk, if you run at the same exact clock time, when that millisecond thing comes around again.
No, you're right, but you would reduce it.
You reduce it, yeah.
Yeah, so now you can do the millisecond time, and then you could probably do the current lunar phase. You could throw that in there.
It's kind of interesting. You could.
The temperature of a grain of sand in Tamil. in joules. Or Kelvin, rather, in Kelvin. All right. That was kind of fun, actually. Okay, well, not the direction I was planning on going, but very related to what we're talking about. All right, let's take 5 minutes, stretch, whatever, run to the restroom, and we'll come back and go from there.